Hi everyone, this is Maverick Paul, the chemistry guru. Now in this video, we want to discuss the thermal decomposition of group 2 metal salts. Now let us consider the thermal decomposition of three different group 2 metal salts, our carbonates, nitrates, and hydroxides. And we want to see the similarity between the decomposition temperature for our group 2 metal salts. The first one that we want to consider is our carbonates. Carbonates decomposition essentially follow this balance equation here. The carbonate will dissociate to give me the metal oxide and CO2 gas as the product. Now, you notice in order for me to decompose this to form metal oxide, what must happen is somehow some of the bonds within the carbonate has to be broken. So I break some of these bonds within the carbonate and I can release the carbon dioxide gas as the product. And what we have here are the thermal decomposition temperatures for our group 2 metal carbonates as we go down the group. Magnesium carbonate, the decomposition temperature is 350 degrees Celsius. Calcium carbonate, the temperature starts to go up, 840 degrees C. Strontium carbonate, the temperature is higher, 1100 degrees Celsius. Barium carbonate, the decomposition temperature is also higher. It is between 1000 to 1450 degrees Celsius. So notice, as you go down this group, it is harder and harder for you to decompose the carbonate, or it requires a higher temperature for decomposition. Now next, let's look at nitrates. Nitrates, the decomposition will follow this balance equation. You have two of this metal nitrate and it will decompose to give me two metal oxides, 4 nitrogen dioxide, which is a brown gas, plus oxygen gas as the product. So again, in order for me to decompose the nitrates, you notice some of the bonds inside these nitrates must be broken so that it can form the oxide and combine with the metal, and you get these two different gases, our nitrogen dioxide and oxygen. And if I look at the temperature for decomposition of the group 2 metal nitrates, you notice there's a similar trend. Magnesium nitrate, the decomposition temperature is about 330 degrees Celsius. Calcium nitrate, the thermal decomposition temperature starts to go up, 500 degrees Celsius. Strontium nitrate is 570 degrees C. Barium nitrate, it is slightly higher, 620 to 670 degrees Celsius. So very similar to what we have encountered for carbonates. Carbonates, as you go down the group, the thermal decomposition temperature increases. Nitrates, the trend is also similar. The decomposition temperature for nitrates will also increase. Now how about hydroxides? Hydroxides, if I decompose hydroxide, I'll end up with the metal oxide plus water as the product. Again, in order for me to form this oxide, I need to break this OH bond and it undergoes some form of rearrangement. It ends up with oxide and water as the product. And if I look at the decomposition temperature for hydroxides, you notice the trend is exactly the same as that for nitrates and carbonates. Magnesium hydroxide, 330 degrees Celsius. Calcium hydroxide, 520 to 580 degrees C. Strontium hydroxide, slightly higher, 500 to 850 degrees C. Barium hydroxide, the temperature is also higher, 780 to 800 degrees C. So again, what we notice is the trend is very consistent. As we go down the group, the salts require a higher and higher temperature for us to decompose the salts to get oxide and some gases as the byproduct. So of course, the question now is, what is the reason for this increasing thermal decomposition temperature, and what is the reason for this increasing thermal stability for the group 2 metal salts? Alright, so this is what we want to answer. Why the decomposition temperature or the thermal stability will increase down group 2. Let's use carbonate as an example, because the decomposition to form oxide and carbon dioxide, it is easier for us to visualize, but essentially it is the same for nitrates, hydroxides, and all the other salts that can be decomposed. Now, if I look at the interaction between the cation and anion, there are two ideas that we want to consider. The first idea, it is the charge density of the metal cation and the polarizing power. Now Mg2+, because of the high charge and small size, we say that it has a high charge density and it causes the polarizing power for this metal cation to be high. So we have this here, Mg2+ has a high charge density, which is directly related to charge divided by size, high charge plus 2 charge, and the size, if I compare group 2 metals, the size is small, and it has a high polarizing power. Now, so what if it has a high polarizing power? Now, the polarizing power of the metal cation is the ability for this metal cation to distort the electron cloud of a neighboring anion. So if this Mg2+ has a high charge density and it has a high polarizing power, so what it can do is it can pull the electron cloud for carbonate towards itself, and there's a distortion of this electron cloud. So what this Mg2+ can do is it can actually pull the electron cloud for carbonate, and some of these electron clouds, which is supposed to be surrounding our carbonate, is now pulled towards our Mg2+. Now, the consequence of this distortion of electron cloud is the electron cloud is actually used by carbonate, that means this carbon and this 3 oxygen, to interact within itself. So this electron density is used by the carbon and 3 oxygen to interact within itself. So therefore, each of these carbon-oxygen bond will have a certain strength, will have a certain stability. Now, what happens when you have this Mg2+? This Mg2+ is trying to steal electrons from the carbonate. So if the electron is being distorted and is being pulled away from the carbonate, then you have less electron density to interact within these atoms inside this anion. So the bonds within this anion will start to weaken because the electron density that is supposed to be used by all these atoms within this anion is now being taken away by Mg2+. I have less electron density for all these atoms to interact within themselves. The bonds within this anion would weaken. If it weakens, then it means that it requires a lower temperature for me to break this bond and to release the CO2. So we have this here, there's the distortion of the electron cloud because of this highly polarizing Mg2+. So the bonds within the anion will be weakened and it is easier for me to break. That means less energy is required for me to break one of these bonds. If let's say this CO bond is broken, then you notice what I've highlighted here, this portion will just be released as carbon dioxide. Then this oxygen will combine with this Mg2+ to form our metal oxide. So now that we know that the decomposition temperature or the thermal stability of group 2 metal salts is related to the polarizing power of the metal cation, what happens down the group and what is the difference in the trend down the group? Now we know that down group 2, the size of the cation would increase because the number of inner shells will increase. So therefore the size of the cation will get bigger and bigger. So what this means is charge density, which is Q divided by R, charge divided by size, it will decrease because you have a bigger denominator. So if charge density decreases, the polarizing power of the metal cation would also decrease. So there's a weaker ability for the metal cation to distort the electron cloud of a neighboring anion. So the electron cloud of the anion, it will be distorted to a smaller extent. So the bonds within the anion, it would be weakened to a smaller extent. So what this means is it is more stable to heat, or I need a higher temperature to decompose the salt. That is the reason why consistently, if I look at carbonates and nitrates and even hydroxides, you notice the decomposition temperature for all these group 2 metal salts will increase as you go down the group because the polarizing power of the metal cation, as I change from Mg2+ to Ca2+ to Sr2+ to Ba2+, the polarizing power decreases and there's a weaker ability to distort the electron cloud of the anion. So the bonds within the anion is stronger. It requires a higher temperature to decompose this salt. So the decomposition temperature of group 2 metal salts will increase as you go down the group. Alright, so that was the discussion involving thermal stability and the decomposition temperature of group 2 metal salts. If you have learned something useful from this video, please give me the thumbs up, like this video, and subscribe to my YouTube channel for more weekly video lessons. That's all for now. Thanks for watching.